Hello friends, this is Mechanics C2 paper solution of 2021 physics major students for the physics major students. So BSc first sem. So this paper is set by Dibrugarh University. So this is part 2. This is part 2. So in part 1 we have solved from question number 1 to question number 2C. So in this part 2 we are going to solve from the question number 2D, right? From question number 2D we're going to start from question number 2D, then remaining questions will be solved in the third part. Okay, so now before we start, please subscribe the channel if you are new to my channel and share with your friends. Hit the thumbs up button and also hit the bell icon so that when new video will be uploaded you will get notified. So now let's start. So here is the question number 2D. Distinguish between inertial mass and gravitational mass. And these are the difference here I have written. So here you can see that difference between inertial mass and gravitational mass. So inertial mass relates how a mass responds to an external force. Okay, and it is measured when the object is in motion due to the applied force using Newton's second law, right? So that means suppose this is an object, when you apply a force, then how this mass responds to this external force, that is the inertial mass, and it is measured in when it is this object is in motion due to this force F, using the Newton's second law, right? F equal to ma, right? So now you see, and in the next gravitational mass relates to how a mass responds to the force of gravity, right? The force of gravity, it is measured when the object is in the motion due to the gravity using Newton's law of gravitational, Newton's law of universal gravitation. Okay, so these are the differences between the inertial mass and gravitational mass. Okay, so now let's move on to next question. Here you see, define damp oscillation and forced oscillation. So definition of damp and forced oscillation already discussed in 2019 question paper of mechanics. So that's why I'm not gonna write this answer again. So if you have watched those videos made on 2019, you might have got. Okay, so I'm not gonna write these answers again. So now let's move on to the next question. So here you see, all simple harmonic motions are periodic, but all periodic motions are not simple harmonic. So explain the statement. So you see here, all simple harmonic motions are periodic, but all periodic motions are not simple harmonic, because you see simple harmonic is a special case of periodic motion. Let me tell you how. Because simple harmonic motion are periodic as they are repeated identically after equal intervals of time, right? So in case of periodic motion, the motion repeated after a regular interval of time, and this happens in case of simple harmonic motion also. So that's why simple harmonic motions are called periodic motions, right? Simple harmonic motions are periodic motions, but not all the periodic motions are simple harmonic, because you see as a motion to be simple harmonic, this object moves in simple harmonic motion. Object moves to and fro motion about a mean position, but not in all the periodic motions object moves to and fro about the mean position. So for simple harmonic motion is so simple harmonic motion is a special case of periodic motion, right? So let me give you an example. Suppose you consider let us consider two cases. One is case of simple pendulum. So simple pendulum, when it oscillates, so it moves to and fro motion about its mean position, right? And its motion also repeated after a regular interval of time. That's why it is simple harmonic motion as well as periodic motion, right? As well as periodic motion. But if you consider the case of Earth revolving around the sun, then this motion also repeated after a regular interval of time, but the Earth doesn't move to and fro, right? It just repeated its motion, but it doesn't undergo to and fro motion. That's why it is periodic but not simple harmonic. So hope you have understood this. So now let's move on to next question. So here you see what are the transformation equations. Establish the set of equations for Galilean transformations. So what are its uses? So here you see this is the definition of transformation equations. The transformation equations are the equations which relate the position and time in two different inertial frames. Suppose we have two inertial frames. One is suppose S, another is suppose S dash. S dash is moving with velocity v with respect to, it is moving with constant velocity v with respect to the inertial frame S, suppose along x direction. Then what happens? Let coordinates and the time of an event when the S frame of reference is used be denoted by x, y, z and t, right? And let the same event in S dash frame of references to be denoted by x dash, y dash, z dash, t dash. Suppose any event, let me consider here, suppose any event occurs here. So with respect to this inertial frame of reference, the this S inertial frame of reference, so let me write here. So this E, the coordinate of this event E is given by x, y, z and the time is t, and with respect to S dash it is x dash, y dash, z dash and time t dash, right? We have taken this way. Let us choose our axis so that x and x dash axis is to be both parallel to the velocity v, and y dash axis is be parallel to y and z respectively. Let us count the time for the instant at which the origin of the coordinates O and O dash momentarily coincide. So now you see initially when t is equal to 0, these two coordinates of these two frames, you see origin of these two frames, suppose O and O dash coincide, right? As time passed and this S dash frame moves forward, right? We can assume that way. Then after a time t, frame S dash is separated from S by a distance v into t, right? So this is the frame S, and when after a time t, this S dash is in this position with the origin O dash and here O origin. So when they were at you see when t is equal to 0, these two the origins of these two were coincides, right? This at t is equal to 0. So after time t, it's moving with velocity v. After time t, it's got this position, and distance traveled by this frame S dash, if it is moving with velocity v and time t, then distance is equal to velocity into time. So distance traveled by this frame s dash with respect to s will be given by v into t. So it is a basic concept. So I hope you have understood this. The coordinates x, y, z, t of any point situated in space with respect to s frame of reference and its coordinate x dash, y dash, z dash, t dash, who is with respect to s dash of frame of reference may be seen to be related, referring to this above figure, okay, by the following equations, okay, by these equations, and these are the Galilean transformation equations, right? So now you see, use of this Galilean transformation equation is nothing but the Galilean transformations are used to transform between the coordinates of two reference frames which are in constant relative motion. So this is the answer to question number 3. Now let's move on to next question. So here you see, what is conservative force? So definition of the conservative force is this. So a force acting on a particle is said to be conservative if the work done by this force in moving the object from one point to another point is independent of the path. Okay, so if you are doing a work by application of a force on a particle, if you are or on an object, and it is moving from one point to another point, and the work done by this force, if it doesn't depend on this path, then it will be called conservative force. So hope you have understood this concept. Now you see, F is the conservative force we have considered according to the definition of potential energy, right? So now let me consider this way, that this F is the force, conservative force, that is acting on a particle. So acting on a particle, suppose this is the particle at P, right? This force is acting on this particle, and it moves P, move this particle from P to Q, suppose, okay, and work done by this force F acting on this particle for moving this particle from P to Q is given by the definition of potential energy given by this expression, right? So let me mention here one thing. So we have considered this F force acting on a particle to move it from P to Q. So we have assumed like this, right? So then by definition of the potential energy, we should get this relation, integration F dot dr. This written bold means this is these are vectors, right? So potential is not vector, just force and dr are vector, and if you integrate it from P to Q, then you should get Vp minus Vq, right? So Vp is potential at P, that is Vp, and Vq is potential at Q, right? So dV is the increase in potential energy of a particle when it suffers a displacement dr. Then we can write, if the increase in potential is dV, then we can write dP minus Vp minus Vq is equal to dV, right? So then if you use this relation here in the first equation, so then you will get this relation, right? So which implies dV is equal to minus F dot dr, right? F dot dr. This equation simply indicates that the work done by conservative force is equal to the corresponding decrease in potential energy of the particle, right? And displacement dr may be expressed as it is a vector, so it can be expressed as I dx, j dx, k dx, I cap. These are the unit vectors, j cap and k cap, right? So now total increase in potential energy of the particle as a result of displacement dr can be expressed as dV, which is equal to del v by del x dx, del v by del y del v by del z dz. So this is suppose equation number 2, and this was equation number 1. Then this equation, these three terms, first, second and third terms, represent increase in v, that means potential energy on account of increment dx in x, dy in y, dz in z, right? So that means, so increment along x-axis is dx, increment along y-axis is dy, increment along z-axis is dz. Okay, so due to this increment, so these three terms respectively represents the increase in v, right? That is what they are trying to say, right? So now you see, so dv can be written as del v dot dr, right? Del v is the del operator, this is the del operator, I cap del by del x, j cap del by del y, k cap del by del z. So hope you have understood this. I hope you know about the del operator, right? And if you substitute the values of the dv from 1 in 3, right, from 1 and 3, 1 in 3, then you will get f dot dr, this vector f vector dr is equal to negative gradient of v dot dr, right? So you will get this. So that means what we have done, you can see here clearly, this dv is replaced by minus f dot dr, right, from 1, right? So hope you have understood this. This is equation number 3, right? So we have got this relation, and from this relation implies f vector plus grade v dot dr is equal to 0. So here, dr is very small but not equal to 0 in this case, because displacement is taking place, right? So the things that can be 0 is force plus this grade v, right? That can be equal to 0, and if it is equal to 0, then f must be equal to negative gradient of v, and so f is the conservative force, and so that is negative gradient of potential, v is the potential, right? So that's how we can prove. So hope you have understood. Now so our next question is, determine the coefficient of viscosity of alcohol from the following readings in the experiment with Poisson's apparatus. So here are the readings given. So first I mention the given readings, okay? And d stands for density. Here density is given, length of the tube is given, L, right? And the volume, rate of volume, okay, of liquid, volume of alcohol, at what rate it flows through the tube, that is given. V is equal to 10 into 10 to the power 6 meter cube per minute. So I have converted this one into meter cube per second, right? Then radius is given, radius of the tube is given, so convert this one into meter, given in centimeter, convert this one into meter. So height of the alcohol had given, right, h. So here is the Poisson's equation, v is equal to pi p. P is the pressure difference, that's given by h d g. D is the density here. Now g is the acceleration due to gravity, that is 9.8. So now if you put the values here, you say 3.14. If you put the values of this these parameters here in this equation, d, l, v, r, h, eta, we are to find eta, that is coefficient of viscosity. So if you put those values here in this formula, then you will get this eta. This is the coefficient of viscosity of alcohol, right? And this is the answer. So this is nothing but the coefficient of viscosity, of alcohol, right? So this is the required answer. So hope you have understood this. Now let's move on to the next question. So here is the next question. Young modulus and bulk modulus for silver is given, right? So this is the Young modulus, you can take it as Y, and this is the bulk modulus, you can take this one as B, right? Sorry, not B, we are taking this one as K, right? K. And we need to find a Poisson's ratio, which is represented by sigma, right? Sigma. So these are the given Young modulus and bulk modulus. We have to find sigma, right? So Poisson's ratio. So these three terms are related by this equation: y is equal to 3k into 1 minus 2 sigma, right? And if you simplify this, then you will get sigma is equal to this, right? And if you put the values, then you will get this answer, right? So this is the Poisson's ratio of silver. So that's how we can do. So instead of this question, another question is given as or. This is the question. Let me show you. So this is the question: define gravitational potential so that the gravitational potential at the center of the solid is 3/2 times that on the surface, right? First, let me write the definition of what is gravitational potential. Let me write the definition here. So here is the definition: the work done in moving a unit mass from infinity to any point in gravitational field of a body is called gravitational potential, right? This is the definition of gravitational potential. Now let us consider the point P lie inside a solid sphere of radius a, radius small a, right? This is the point P. Here you can see this is the point P in the diagram. So this is the point P, right? So inside the solid sphere, this is the sphere, right? And at a distance r from the center O, so this P is at a distance of r from the center O. So this distance is r, right? Let us draw a concentric sphere through P. So we have drawn another sphere through P. So you can see this sphere is drawn through the point P, another sphere through P, concentric sphere, right? Center is the same. The point P lies on the surface of the solid sphere of radius r, right? And inside the spherical shell of internal radius r and external radius a, right? So if you consider this is a shell, so that means here you see this is the sphere, this is the point inside it, and we have drawn another sphere through it. So now it's become a shell of internal radius r and external radius a, right? So this P is within this shell, we have considered this here. Now you see the potential V1 at P due to the inner solid sphere. If you consider the inner solid sphere, so potential at P due to the inner solid sphere is, suppose V1 we are taking here. So its mass will be, if the density is density of the solid, density of the solid is suppose rho, then the volume of this inner sphere, this sphere that we have drawn through the point P, if its volume, if internal radius is r here, you see, so its volume will be 4/3 pi r cube, right? 4/3 pi r cube. If you multiply density with volume, then it's gonna give you the mass, right? And if this is the mass, then potential should be V1 is equal to minus capital G mass by the divided by the distance between the point from this solid. So here capital M mass is given by 4/3 pi r cube rho, right? So now you see rho is the density, it is already written here. Now here what we can do, this r cancels r cube to give r square, right? So this equation becomes this, right? This is suppose equation number 1, right? To determine the potential at P due to outer spherical shell, let us consider it to be divided into number of thin concentric cells consider one of radius x and thickness dx. So we have considered, let us divide this cell. Here you see, let me show you again. So we have divided this cell. So this is the P point here, and this is the sphere with the external radius. So this cell is divided into small cells of thickness dx, right? We have imagined that way. Now the volume of the cell should be considered here. Let's go to the next slide. Here you see the volume of the cell will be surface area and thickness, right? Surface area and thickness will give you the volume of this cell that you have assumed here. This is the cell, this is P here, right? This is P, and you have considered another cell with the radius x, right? With radius x and thickness dx. Thickness is dx, right? So then what will be the volume of this cell, right? Then volume of this cell is given by the surface area, that is internal surface area, that is 4 pi x square, right? And as it is very thin, thickness is dx, so you can just find the volume of this cell actually. So here volume of the cell, it doesn't represent this entire volume, right? So it doesn't represent it here, only this portion is considered, right? This portion is considered, right? So in this case, and that volume will be given by surface area into thickness, so that is 4 pi x square into dx, right? And so its density will be given by density of the solid sphere we have considered rho, so that's why mass will be given by volume into density, right? So now the potential at any point within the spherical cell is the same as any other point on its surface, right? So potential at P due to the thin cell considered is given by minus capital Z mass of the cell by radius of the cell, and that is equal to this. So here this x cancels x square to give x, so that's why we have got this relation, right? Now to get the potential at P because of the entire cell, the solid sphere, so we need to integrate this from the radius r to a, right? From r to a, then we get the potential V2 at P due to the cell of internal radius r and external radius a, and hence V2 is given by this integration from r to a minus z dot 4 pi x dx rho, right? And after integrating this equation, we have got equation number 2. This is V2, right? So you hope you know how to perform integration, right? So now total potential at P due to the whole sphere will be given by V is equal to V1 plus V2, and from equation number 1 and 2, in equation number 1 what we have got, so this is the equation number 1 V1, right? And from equation number 2, this is the equation number 2. If you put the values of V1 and V2, that is what we have got here, you can see, using 1 and 2. And if you simplify this, then you will get V is equal to this one, right? This is equation number 3. So here 4 by 3 pi a cube rho, this is nothing but mass of the sphere. So 4 by 3 a cube rho is the density, and 4 by 3 a cube is the volume of the solid sphere, that whole sphere that we are taking here. So at the center, you see, at the center r is equal to 0, so if you put here r is equal to 0, then this equation number 3 becomes V is equal to 3 by 2 minus capital G capital M by A. You can write this way. This is equation number 4. So let me write the same equation in equation number 4 here. So I have written this one. This is the potential at the point at the center of the sphere. This is the potential at the center of the sphere. Now at the surface of the sphere, you know that here you see at the surface of the sphere, that means we have taken the radius of the sphere A, right, small a, this whole sphere. If you move on to the diagram here you see this is the diagram. We have taken this radius A, right, we have taken this radius A. So at the surface, if you consider the point at the surface of the sphere, then you have to put this small r is equal to small a in equation number 4. In equation number 4, this is the equation number 4. This is equation number 4. So let me write the equation number 4 on the other slide also. This is the equation number 4. Here you can see this is the equation number 4. So if you put this value of r here, then you will get, sorry, this was equation number 3, not 4. So if you use this value r is equal to a in equation number 3, this third equation becomes V is equal to this one, right? And if you simplify this 2 will cancel, then a square cancels a cube to give a. So here you will get the result. This is equation number 5, right? So comparing 4 and 5, and this equation number 5 gives potential at the surface of the sphere, and equation number 4 gives the potential at the center of the sphere. So comparing 4 and 5, you can say that gravitational potential at the center is of a sphere is 3 by 2 times that on its surface. So you can see clearly, if you see this part of this equation number 4, it is equal to the right hand side of this equation number 5, which is the potential at the surface, and 3 by 2 times of that potential at the surface is equal to the potential at the center of the sphere, right? So hope you have understood this. Now let's move on to next question. So here it is given that what is the center of mass of a system of particles. So first let me tell you the definition of center of mass of the system of a particle. The center of mass of a system of particles is defined as the point at which all the masses of the system of particles appear to be concentrate. That means it can describe the translatory motion of all the particles of the system, right? So that is all about the center of mass. Now next part of the question is, so that in absence of any external force, the velocity of the center of mass remains constant. Let me prove this one. So let's move on to next slide. So we have considered a system motion of center of mass. Here you see, consider a system of n number of particles of masses respectively m1, m2, m3 dot 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 up to mn with position vectors r1, r2, r3 dot 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 so rn respectively. Then the position vector of the center of mass, that rcm, is given by this expression, this result, right? Here you have got summation mi, this is r vector, ri vector by summation mi, right? So hope you have understood this. This is position vector of ith particle, that is ri. So that's represent. So here you see this is the position vector of the center of mass, and differentiate this equation number 1, then you will get, if you differentiate the position vector with respect to time, then you get velocity, right? Then you get velocity. So if you differentiate the position vector of center of mass, then you will get the velocity of center of mass, right? Simply. So that is velocity of center of mass is given by this equation, drcm by dt, right? And that rcm we have obtained from this equation number 1 is summation mi ri by summation mi. If you use that relation here, then you will get this summation mi dri by dt, right? And dri by dt, that's going to be vi. So Ri is the position vector of ith particle. So if you differentiate it with respect to time, then you will get the velocity of ith particle. So hope you have got this. So mass into velocity, that gives momentum. That is sum. Here we are taking the summation, right? Momentum of all the particles, sum of all the particles pi. So here you see sum of pi, that means that's going to give you the sum of momentums of all the particles, and divided by a sum of the mass of all the particles, that's total mass of the system. That is what velocity of the center of mass. Now you see this vi is the velocity of pi is the momentum of ith particle of mass mi. Vcm is the velocity of the center of mass. So now let's move on to the next slide. So from equation number 1 we have got that momentum pi is the total summation pi is the total momentum, right? So we have got from here that should not be equation number 9, that equation number 2. Sorry, I have made a mistake here. That should be equation number 2. Okay, in equation number 2 you can see this term, that summation pi, that is nothing but the total momentum, right? So equation 2 implies that Vcm, that means velocity of the center of mass, is given by this. Here you see, we know that mass is constant already, and in absence of external force, momentum is also constant. That summation pi is also constant. So if momentum is constant, and so this velocity of the center of mass is also constant, as the momentum is constant in absence of external force, then this momentum is also constant, and mass is always constant. We know that fact. This is a fact, right? So that's why this velocity also constant in absence of external force, if the external force is 0, right? So that's how we can write this answer. So hope you have understood this. Now you see remaining questions will be completed in the third part, so stay connected and hit the bell icon so you get notified when the third part will be uploaded. Thank you for watching. See you in the next video. And if you are new to my channel, please subscribe the channel if you haven't yet subscribed, and also share with your friends. Help me to grow my channel and inspire me to create new contents, and inspire me to work hard for you. So thank you.